Okay, hello and welcome to the Radical Sim Homework Help Livestream. If you have homework questions about math or physics, or other sciences possibly, you can put those in the chat and we will try to help you solve them live. So, in the meantime, I'm just going to be solving some random math and science problems to pass the time, but feel free to interrupt at any moment. Let's see here. Let's start with some physics this time. Okay. So we need to calculate the escape velocity for a rocket. Now to do that, we need to consider what escape velocity means. Basically what we want to do is give our rocket enough kinetic energy that it can escape the potential energy well around the Earth. So if we get it far enough away, moving fast enough, the Earth won't be able to pull it back down. So what we really have is two cases when we're on the surface. Right up a little higher. So when we're sitting on the surface of the Earth, and when we get to effectively infinitely far away from it, at that point the gravitational force will be basically zero. So what we're going to do is compare the energies at these times. So we're going to assume no air resistance on while we're leaving the atmosphere. So we should have all conservative forces in play, being gravity, and we're also not going to consider the complexities of rocket propulsion. We're just figuring out how fast it needs to go. So we're going to say that the energy it has initially while it's sitting on the Earth's surface is equal to the energy it will have as it goes out to infinity. And then we'll take stock of what kinds of energy we have. We have kinetic and potential energy initially, and then we'll have kinetic and potential energy at the end. So I think we need to so we're going to assume that at the beginning our rocket is in motion. So we have V initial taking us upwards, and once we get really far out away from the Earth, we'll have V final being 0. So once we get far enough away, we can completely stop moving, and the Earth will still not be able to pull us back down. And so we can get these two kinds of energy using our formulas. We'll have 1/2 mv initial squared plus, we're actually gonna, normally we use like mgh to get potential energy from gravity, but we're actually going to use a different formula. We're going to take the formula for the force of gravity multiplied by the radius that we're at. So that's the radius of the Earth. If you multiply by it, we just divide by it one time. And I think we should give those different signs there. Then at the end, our kinetic energy will be 0 because we said we'll have 0 energy there. And keep that negative. G, mass of the Earth, mass of the rocket divided by, we'll say R final squared, and we'll times it by R final, which will cancel the squared. So now we should be able to solve for the initial velocity and take the limit as this radius goes to infinity, and that should give us what we're looking for. So we'll add this to the other side to get 1/2 mvi squared. So I'm going to write that as m over 2 equals g, mass of the Earth, mass of the rocket. I don't know why I wrote those like they were going to be on a fraction, because I'm going to split it up. We'll put the negative sign in front, and we'll have 1 over our final. Oh, actually, hold on. So this term would be negative, that one would be positive. So we'll have 1 over the radius of the Earth minus 1 over the final radius. There's no negative there anymore. So VI is going to be the square root of 2 over the rocket mass, so that's going to cancel out. So we'll have 2g, the mass of the Earth, 1 over the radius of the Earth, minus 1 over the final radius. So we're almost there. So if we take the limit as that final radius goes to infinity, nothing else is changing here. We just have this. If that goes to infinity, 1 divided by it will go to 0. So really, this will be the square root of 2g times the mass of the Earth divided by the radius of the Earth. And then we can try to get some numbers out of that. And note here that the escape velocity is actually completely independent of what the rocket's mass is. It only depends on the mass of the Earth and the radius of the Earth, or whatever point you're launching from. If you know, maybe start up on a mountain or something. Okay, so let's try to plug in some numbers now. We've got the square root of 2 times, I believe that's 8.85 something. Nope. 6.67. And we'll have a 10, oops. We'll have a 10 to the minus 11 from that out of the end. For the mass of the Earth, we'll have 5.97. A 10 to the 24. And for the radius of the Earth, we'll have 6.371 10 to the 6th meters. So a positive or a negative 10 to the 11 on top would be a positive 10 to the 11 on the bottom. So altogether we're going to have a 10 to the 17 on bottom. Or 10 to the 24 divided by 10 to the 17 will give us 10 to the 7. Let's calculate the product of all these significant digits. We get 11,000 meters per second. I can double check that. So the value I'm seeing on Google is 11,186 meters per second. So we are like spot on. That is a very, very small percent difference. I imagine this is probably just calculated with more more decimal places of precision or something. Some amount of rounding that I did threw it off by a little bit. Cool. So that tells us we did this one right. Ah, bestowal pants. A calculus question. Go ahead. I'll hold off on starting a new problem. infinite series. Does that look right? And are we supposed to evaluate this? Are we supposed to find out if it converges? What's the question asking us to do with this series? Okay. So, want to find and classify convergence. Let me grab my calculus book. Before I crack that open, I'm going to write down my ideas. I'm pretty sure the one that works most of the time is the ratio test to find convergence. Let me look that up again just to double check the details of it. Because the different tests for convergence have, I'm sure you know this since you're in the class, but they have different conditions for how you interpret the result. Ratio test, here we go. Well, it mentions the ratio test, it doesn't tell me the theorem that gives all the details about it. Here we go. Okay. So if we're going to take the limit, the absolute value of this to the n plus 1 over that with n, doesn't ask for a finite number. I did the absolute value of an and summed it and got diverging, but I can't figure out the sum of an. Yeah, I don't think we'll be able to find a number. Like, I don't think we can say this equals something. Probably if we had a calculator or some computer code to just evaluate term by term, we could find, you know, for example, maybe it equals like 5.6235, and the more terms we evaluate, we would get more and more decimal places of precision. But I don't think there's a mathematical way that we can just find the number it equals. So if L is less than 1, then our series converges absolutely. If L is greater than 1, the sum diverges, and if the limit equals 1, we get no result. We can't make any conclusions about it. And I've taken up most of my board space just by doing that. So let me rewrite the sum a little bit smaller up here so we have it to look at. So we're going to take the limit as n goes to infinity of, so first we'll plug in n plus 1 on the top, so that's 4 times n plus 1 minus 5 with negative 1 to the n plus 1 minus 1. That's all on top, and then we'll just copy that exactly for the bottom. Negative 1 to the n minus 1 over 4n minus 5. Close that absolute value. So we're dividing by a fraction, so we'll flip it to multiply by the reciprocal. We'll get 4n plus 4 minus 5, negative 1 to the n, and then from the bottom we'll have 4n minus 5 over negative 1 to the n minus 1. So 4 minus 5, that'll just be a negative 1. Negative 1. How did I get the limit? I have not got the limit yet. If you're talking about how I filled this in, that's using the definition for the ratio test. So where the term inside of our sum is called an, we plug in n plus 1 and put that on the top of a fraction, and then we take the regular form an and put that on the bottom of a fraction. Stick it all inside absolute values, and then we'll take the limit as n goes to infinity. And then we'll simplify the limit, and once we figure out if it's one of these cases, we'll know more about how the series converges or does not converge. Okay, so negative 1 to the n, negative 1 to the n minus 1, those, let's see, n minus 1 is 1, so we would get negative 1 to the first power overall. So if we're left with negative 1, how come the plus 1 is in the exponent? I was taking where the n was at in our an term, and everywhere that n showed up, I just put an n plus 1 instead. Like right here we had regular n next to the 4, so I plugged in an n plus 1 into that spot. So, with a negative 1 inside of absolute values, the absolute value of negative 1 will just be 1. So that's going to finally disappear. Then I'm just going to rewrite this over here. Save a little space. Okay, and now I'm realizing we're not going to get very far with the ratio test, so we're going to have to try another one. Because when we have a limit going to infinity of a rational function like this, if we have the same power of our variable on top and bottom, n to the first power and n to the first power, the limit evaluates to the coefficients of those variables. So we get 4 over 4, which is equal to 1. So that means we get no result from the ratio test. So we actually need to try something else to find out how this series converges. I always default to the ratio test because it is usually the most useful one. Let's see. Maybe we could try the root test. Maybe not. Use this unnamed test. I would ask you what the name of it is, but if it doesn't have a name, so I'm not sure which one it would be. We tried the ratio test. That didn't work. There's the root test, the integral test, the limit comparison test. Does that one? Let us determine conditional or absolute convergence. Oh, alternating series test, of course. Okay. So I think we can find that it does converge using the alternating series test. Oh, okay. It states that, not this anymore, I'm reading your comment. It states that if the sum, the absolute value of an converges, then it converges absolutely. And if the sum of an converges conditionally, if the sum of an converges, and the sum of, oh, okay, yeah. Right. So if we look at, maybe I'll call it S2 or something. So we have the same summation, but we do it for n minus 5, negative 1 to the n minus 1, all in absolute values. So if that converges, and this sum converges, then we would have absolute convergence. I think we with the alternating series test, I think we can find that the original one converges, and then we'll see what we can do for this one. With the alternating series test, we want to have an decreasing, or like the absolute value of an decreasing, and when we have 1 over 4n minus 5, this 4n is going to keep getting bigger, so the, the n plus 1 term will be less than the nth term because you're going to be dividing by a bigger number every time. And then if the limit of that absolute value of an as n goes to infinity is 0, which it is, because if we plug infinity into there, we're dividing 1 by infinity. So with those two pieces, we know the original sum converges. And I guess that would be conditionally. So now we need to look at what you mentioned to determine the absolute convergence. Okay, let's see here. So the absolute value of an, I'm just going to try to simplify that off to the side here. The negative 1 to whatever power will just become a 1. So this should be positive most of the time. The only problem is at n equals 1, because we would have 4 minus 5 being negative 1. But after that, we would have 8 minus 5, which is positive, 12 minus 5, which is positive, so on and so forth. So I think I'm not sure if we need to do this, but I think we can say that like 1 plus the sum from 2 to infinity of 1 over 4n minus 5 is equal to that, because if we, I don't think we can get that to work with the n equals 1 term, since they would evaluate to negative 1. We need to take the absolute value of that and put it in front, and then we can work with the rest of the sums starting at 2. So really now we want to see if this converges, so we'll say that's S3. For S3, how can we find its convergence? I think the ratio test will again fail us with this one, because we'll still end up with 4n on the top and 4n on the bottom. So we would not get any information from that. We could, for the first term, like, you know, when n equals 1, then the absolute value of 4n minus 5 is 4 minus 5 is negative 1, which is 1. But then once we get to n equals 2, 4n, so that could be the same as 5 minus 4n. That would work for n equals 1. But once we get higher than 1, we have 8 minus 5, which is 3. And if we said 5 minus 4 times 2, we would get, maybe that would work, 5 minus 8, which would be the absolute value of negative 3, which is 3, and those are equal. Maybe that will work. Let me try a couple more to convince myself. So n equals 3, if we did 4 times 3 minus 5, that's 12 minus 5, which is 7. And if we did 5 minus 4 times 3, that's 5 minus 12, which is negative 7, which is 7. Yeah, I think that would work. I'm not gonna trust my gut on this one. I'm gonna look at a graph of it on my calculator here, because this can calculate, you know, like the first 10 examples way faster than I can. Okay. How do I do an absolute value on this thing? I don't actually know. I guess square it and take the square root. So the square root of some stuff, 4x minus 5 squared, and the square root of 5 minus 4x but squared. So table start at 1, delta table 1. Yes. So we'll work with the first one, 1, 3, 7, 11, 15. Okay. Oh, whoops. Can I change to this one now? The num tab. Absolute value. Beautiful. Also, I entered that one totally wrong. I did 5 times. 5 minus 4x. So here we'll do absolute value of 4x minus 5. Okay, how do I know which one I'm looking at? I guess. Okay, so this is y3. 1, 3, 7, 11, 15, 19. And if we do that one, y1, 1, 3, 7, 11, 15, 19. Okay, yeah. I am now convinced. They are equal. So yeah, we will say that is 5 minus 4n. Oh, wait. Oh, hold on. So what we just figured out by looking at those tables on the calculator is that this absolute value is equal, but I don't think we can make the statement there because that is not equal. This is definitely true, but I don't think we can then just do the series using 5 minus 4n and no absolute values, because then we'll immediately have 5 minus 8 and we'll get a negative number here, which is not what we want. So I think we do still need to work with this separately and just peel off the n equals 1 term and take its absolute value. Yeah. Okay, now how can we see if S3 converges? Maybe we should try the integral test. So if we look at the integral from 2 to infinity of 4x minus 5 dx, or dx over 4x minus 5. Why did I write 2 to 2? Oh, wait, where's the details on the test? It doesn't tell me the theorem in this section. Okay, oh yeah, if the integral converges, the sum converges. So if this integral is convergent, so is S3. So let's let 4x minus 5 equal u, then du dx is 4. Dx over here, put the 4 over there. So this integral is 1/4 the integral from, oh boy, okay. When x is 2, that's 8 minus 5, u starts at 3, and it still goes to infinity. Du over u, 1/4 the natural log of u evaluated from 3 to infinity. So that's the natural log of infinity minus the natural log of 3. But the natural log of infinity is infinity. So this diverges, which means S3 diverges to infinity, which means S2 diverges to infinity. So if, okay, so now we can bring this back to the absolute convergence idea. We know the original sum does converge, but we have just found the sum of the absolute value of the terms diverges. So that means this sum should converge conditionally. It does not have absolute convergence, only conditional convergence. So we'll say the sum of an converges, but the absolute value of an diverges. So the original sum converges conditionally. No problem. Sorry that took so long. It's been a while since I've done one of those problems. We've still got about 10 minutes in the stream if you want to ask another question. Hopefully we can try to do that one a little faster since I wrap my head around all the convergence tests again. I'm gonna go ahead and erase all this. Okay, I think... okay. So, the sum of -1 to the n, 3n over 7n squared plus 1. And I assume that goes from 1 to infinity. And I'm guessing we're doing the same thing. Decide if it converges absolutely or conditionally, or if it diverges. So first we want to see if the original sum converges, then we'll check if its absolute value does. I think we can do this one with the ratio test. So I'm gonna write some of this shorthand to save time and maybe skip some steps if I can do them in my head. We have -1 to the n plus 1. From the bottom term we would have -1 to the n. From the n plus 1 term we would have 3n plus 1, and from the bottom term we would just have 3n. From the top term we would have 7n plus 1 squared plus 1, and from the bottom term we would have 7n squared plus 1. Okay, so the absolute values of the 1s pretty much always cancels out to 1. We want to look at our highest power of 1. Oh, wait a sec. I got those mixed up. That would be n squared. That would be n plus 1 squared. Yeah, because the denominator of the an term would come to the top. Yeah. So on top we're going to have, whenever these two talk, we're going to get 21n cubed out of it. And whenever these ones talk, we'll get also 21n cubed. Oh man, are you serious? Okay, so this limit will be 1, and we'll get no conclusion from the ratio test. I think we can do the alternating series test though. So if we say Bn equals 3n over 7n squared plus 1, we can say that Bn is decreasing. That's one thing that we need. And what was the other one? Oh, the limit of Bn is 0, which it is, because if we have the bigger power of n on the bottom, then as n goes to infinity, this would go to 0. So by the alternating series test, our original sum converges. Now we need to look at the absolute value of the series. And this time I don't think we need to do any special rewriting. It's just going to be that, but without the -1 to the n. And I think we can do that one with the integral test. So I'm going to go ahead and write up here that this converges by AST, so we don't forget. Then here we'll do the integral test as 2, I guess. (3x 7x squared plus 1 dx) we'll let u equal 7x squared plus 1, so du dx is 14x. We'll bring the dx over here. We'll divide by 14, and yeah, we have x dx in the numerator here, so we can absorb that into our du. I2 will be 3 over 14, the integral from 8 to infinity. The integral from 8 to sideways 8 of du over u. So that's 3 over 14, the natural log of the absolute value of u from 8 to sideways 8. And just like last time, natural log of infinity minus natural log of 8, that's going to be infinity. So that means this diverges, so the sum of the absolute value of the terms diverges by the integral test. So because the sum of the regular terms converges, but the sum of the absolute value of the terms diverges, that means the original series converges conditionally again. Okay, cool. That one went a lot faster since I remembered how we're supposed to do these problems. Well, Bestowal Pants, thank you for coming in and asking some questions. That always makes these streams more fun than just solving math problems for myself. And until next time, I hope you have a radical day.